a couple more examples of these, and we need to start integrating over these. After today's class, every problem on the homework you're going to be able to do completely. Nearly every one, actually, we've covered the concept already. But here's a couple of more just illustrations of smooth arcs, contours, if you will. And let's think about how would you parameterize these. So if this is C, let's say C1 here and C2. Since we've got a new day, let's look at these two curves, these two contours. What would C1 look like? Well, it looks like, you can think of different curves, but this is intended to be kind of the simplest curve from the origin to the point 2,4. So what kind of a path would that be? I'm sorry?
X squared.
Yeah, an x squared path. So if you were parameterizing it, you can think of this. You can think of the curve. You can think of the set of all z of t, if you will, where the z value is going to be, well, you want to have an x and a y component. So the x component, if you wanted to take as t, the y component would be, then what, Eric? So if x was t, the y would be, you just said it was t squared, or it would be the x component squared, which is t squared. Yep. So we'd have that. And one of the things when you parameterize a curve, you always want to specify the interval of parameterization. So the t values would go between 0 and 2. We have to specify the parametric interval. Now, if you wanted to, you could say here, instead of z of t, you could write this as z of x. And you could say z equals x plus ix squared. You don't have to use t there. The reason why t is handy is you don't have a preconceived notion that it's representing any particular component. Often you think of x as representing the real component. So, but in this case, you can think of it as t plus it squared. Often we use t, but you could use a different letter if you wanted to. And then if we looked at the other one, again, you might think about sort of the simplest curve here. And again, when you parameterize it, notice as the t increases, that gives us a direction. The direction is important. So similarly, if we wanted a direction here, we want a kind of a simple curve that we could use. In the second case, there's different ways we could describe this. But if we're going to kind of do it similarly, we could say it will be the set of all z of t, where z is of what form? Well, if we wanted to again choose the x as t, sometimes we can do that. What would the y be? Yeah, probably the square root of t. Yeah. So that might be a parametric representation of this curve. And in this case, the parametric interval would go between 0 and 4. We have that. So we've got these parametric curves. We can come up with their representations. If you prefer the letter S or the letter Q or W or whatever, you could use another letter in there. T is a good one. Often can be thought of as representing time. That's why it's often used T, because it's a nice kind of nice kind of active parameter. You can kind of think of it as the time varies from 0 to 4. We're on this curve. So what we're now going to do is we're going to go from parameterizations to how do we integrate? How do we integrate? But now what we want to integrate is, before we were looking at examples, and you saw this on your homework, examples of functions that were complex value functions of t, but now we're going to look at just complex functions of z. And so this is what we're going to define. So given a contour C, and suppose its parametric representation is z of t, where t is between a and b. Suppose we're given that. Then what we're going to do is we're going to set up this, and I'm going to fill this in over here, the definition. But we're going to define the integral over the contour of the function as follows. And so we have to fill this out. We have to see what this is going to look like. So the integral over one of these contours integral over a contour, is going to be the integral. What we're going to do is we want to translate this complex integral to one that involves a parameter, in this case t. So what you're going to do is you're going to think about replacing the z by z of t. What do you think we would replace the dz by? It'll be dt, but it's going to have one additional piece. So you want to think of dz as the derivative of z in terms of t. So we can think of it as z prime of t dt. So what's going to happen is the f of z, we're going to write it this way. The dz we're going to convert to dt, but you're going to have to take a z prime in there. Essentially, we're converting from an integral in terms of z to an integral in terms of the t. This then becomes an integral in terms of the real parameter t. What would the limits be for this integral? T goes between A and B. So this then becomes the situation we had discussed last time when you were working on problem 4 on your homework. These are examples where they were already in this form. What we're now going to do is we're going to take a complex integral in general and we're going to convert it to this form. In order to convert it to this form, what do we need to do to see? In order to be able to set this up, we need to come up with a, what are these called? A contour representation in terms of t, which is called a, what are these? Parameterizations. Yeah, we're going to be coming up with parameterizations. These come up all the time. They come up in Calculus 3. Parameterizations. Now it's possible, actually, there might be even a more correct spelling. This is the one I often use, parametrization. You might see parameterization. I use that one, it's a little bit shorter. That may not actually be a word, but that's what I use. Because I like the verb parameterize, because that's what we're doing. It might be more like parameterize, but I like parameterize. It's a little shorter. Okay, so that's what we're going to be doing. We're going to be doing some parameterizations there. And we're also going to be maybe doing some misspelling of words, but hopefully you're okay with that. Where f here and z prime, these must be piecewise continuous so that the integral exists. So that's the little bit of that's the catch. In order for the integral to make sense, we're going to assume that the integrand consists of continuous functions. So that means we want these functions to be nicely defined. And technically, we want them to be continuous. In order to be able to integrate, these need to be nice functions. Now, when we talk about f is what type of a function? It's a complex function. But when you think about it being continuous, you look at its real and imaginary components being continuous. In this case, the z prime here is the derivative of z. Again, this is complex, but we can think about its components also being continuous. So we want to make sure that the integral makes sense. And so that's where we're headed. This is where we're going to be really for the rest of the course. We're going to be integrating complex functions all the time.